It's a beautiful, crisp morning in Hampshire, and I'm headed out to one of my happy places, my local airfield. Specifically, I'm going to pay a visit to Go UAV, or Golf Oscar Uniform Alpha Victor to his friends. A lovely Sherwood Scout 2-seat microlight built by staff from the University of Southampton Aviation Society as a training aircraft and as an autonomous aircraft systems technology demonstrator testbed. The Sherwood Scout has a wing area of 10.2 meters squared, and it is powered by an engine that develops about 100 horsepower in standard sea level conditions. Now in this video I'm going to try and answer the question of how those two numbers came about for the Sherwood Scout, and more generally, how do we pick these two rather critical numbers in the conceptual design of a fixed-wing aircraft. So there it is, our Scout receiving some tender loving care from staff from the Aviation Society, led by Mem Erbil, busily cleaning it, oiling its various hinges, checking tyre pressures, fluffing the furry dice and so on. Now, as the man in charge of actually building the aeroplane a few years ago from a kit made by TLAC up in Norfolk, Mem is ideally placed to tell us about how lightness was added to the design. It's a remarkably light bit of kit. I mean, it's for an aircraft with a 100 horsepower engine. What's the empty weight?
So it's empty is 280 kilos, and all up with fuel and passengers, you could go up to 499.
So what's the secret of the light weight of the structure?
Well, if you want to come have a look inside, we've got this space frame, which essentially allows us to cram pack all the kit we need inside, whilst allowing to keep the structural integrity. As for the skin of the aircraft, we've gone with something called Oratex, and essentially it's this canvas, which it sounds like a drum skin, doesn't it? It's this is applied on with a glue, and once heated, it starts tensioning itself. So essentially, you're left with these nice clean lines and a nice taut skin, and the same applies to the wings as well.
So with the light structure and the aforementioned 100 brake horsepower Rotax 912 4-cylinder 4-stroke engine up front, Go UAV is quite a capable little aeroplane in performance terms. But back to the original question, why this power rating and why this wing size? There are two key ingredients for fixed-wing aviation to take place: lift and thrust. It follows that sizing the wings and the propulsion system should be an early step in the design process. The starting point for this is the design brief, of course. This has roughly the same headings, regardless of whether we're designing a single-engine microlight like this, a little biodegradable atmospheric sensing micro-drone, a large unmanned freighter, or a passenger airliner. It usually includes a list of requirements in terms of field performance, climb rate, cruise speed, service ceiling, etc. In this video, we look at how these requirements translate into wing size and propulsion performance constraints, and how these can be mapped out on paper or in Python. The ultimate question is, what is the smallest, ergo cheapest and lightest wing and propulsion system that will satisfy the performance requirements? Let's have a look at a graphical method of answering it. So we're looking for the part of the design space that meets all the requirements typically set out in a design brief. Now, we're looking at the design space in terms of propulsion performance and wing size. But it makes sense this early in the design process to keep the analysis essentially scale independent. So we'll use wing loading, which is weight over wing area, and required thrust to weight ratio as the axes of the design space. And we'll convert the design brief into constraint boundaries of the minimum thrust to weight equals some function of wing loading form. We'll demonstrate this, for simplicity, with only a couple of constraints. The same logic applies to the others. Let's begin via a leap of imagination with takeoff. Now, takeoff is a hugely complex and dynamic process in the sense that just about everything varies throughout. The engines may take a while to spool up, the thrust may be a function of airspeed, the acceleration will peak very early on and then typically decline during the ground roll. The balance of aerodynamic forces will be in continuous flux as induced drag begins to rise, with the wings generating more and more lift, which in turn will take more and more of the weight of the wheels that will thus generate less and less rolling resistance. Once rotation occurs, the angle of attack will increase, accompanied by a quick rise in induced drag as we begin the first segment of the climb. A full treatment of all this requires a numerical solution of the equations of motion, but at this very early and very broad stage of the design process, it is common practice to start with something much more expedient. Here is a typical average model of all these variations, expressing an average takeoff thrust to weight requirement as a function of wing loading, ambient density, maximum lift coefficient in the takeoff configuration, G, the ground roll length requirement, dg from the design brief, ground roll CD and CL, and the coefficient of rolling resistance on the tires. Broadly speaking, the first of these terms accounts for the inertia and the high lift performance of the aircraft. The second is a measure of aerodynamic efficiency, while the third accounts for the average thrust required to overcome the average rolling resistance of the undercarriage. With the dominant inertial term linear in terms of wing loading, this minimum required thrust-to-weight ratio constraint will take a straight bite out of the feasible design space, the upward slope confirming that the smaller the wing, i.e. the larger the wing loading, the more thrust will be required for takeoff. So what are typical thrust-to-weight requirements for takeoff? A routine airliner departure will require an average thrust of about a third of the takeoff weight. A sportier display takeoff, like this one, will require a thrust-to-weight ratio closer to about a half, which this A330neo is capable of at the low weights typical of such demonstration flights.
Used for validating the aerodynamics and engine performance of autoland function.
And speaking of sporty departures, this tornado chasing drone developed by students at the University of Southampton requires little more than its own length by way of a ground roll, and it achieves this by virtue of its massive thrust-to-weight ratio of over 1.2. This, in addition to excellent field performance, also makes this party trick possible. Let's look at the cruise requirements next. Now, cruise also has immense complexities, but here we will consider a basic form of the corresponding constraint. This will be the sum of the thrust-to-weight ratio required for overcoming the profile drag and that required to oppose the induced drag. The dynamic pressure Q here encapsulates the cruising airspeed and the cruising altitude demanded by the design brief. Very broadly speaking, a highly loaded small wing is good for cutting down on profile drag, but a larger wing might be better for minimizing induced drag, and this tension is reflected in the shape of the bite taken out by the cruise constraint as we lose more feasible design space to constraint violations. Now, there is a hugely important set of constraints which have nothing to do with thrust at all, and they will be strong drivers of not just the wing area, but also the architecture of the high lift system of the aircraft. And these are the constraints on the 1g stall speed in various configurations. Their importance is mainly to do with the fact that they set the minimum airspeed in various phases of the approach and will thus have a big impact on the landing distance. In its simplest form, This limit on the wing loading can be obtained by dividing the lift equation through by the wing area and plugging in the desired stall speed and maximum lift coefficient appropriate for the configuration we are looking at, clean in this case, and thus a further erosion of the region of feasibility. So, where is our future aircraft most likely to live? Well, the low-cost utopia point of a minimal wing and a minimal propulsor is in the bottom right-hand corner, so we want to be as near to that as possible while staying within the constraint boundaries. So, probably somewhere around this green smudge here. We cannot really pinpoint a single pair of values at this point, because later phases of the design process may impose further restrictions on our engine choice, for example. But a light and low-cost design will most likely live in this sort of region, and it's certainly a good starting point for further analysis. Incidentally, a full derivation of these constraint equations, as well as of those we didn't explicitly mention here, can be found in the notebook section of the ADRPi GitHub page. Here is, for example, the notebook walking you through the derivation of the thrust-to-weight ratio required to satisfy a climb rate requirement. Plotting all this in thrust-to-weight versus wing loading space is nice and generic, but not always the most convenient. For example, if we have a weight estimate already, we can just drop the weights and plot thrust required versus wing area required. Note that this maneuver flips the feasible polygon to the right-hand side. Also, anything with a propeller is usually rated in terms of power. So for turboprops, piston-powered aircraft and electric aircraft, it makes sense to convert the chart into power versus wing area. All we need for this is the ground speed and some estimate of how efficient the propeller is at turning power into thrust. Different constraints will be stated at different altitudes. For example, you could have some field performance constraints specified for a range of different airfields at different elevations. You might have a range of climb rates specified for different altitudes, and so on. Now, unless you're designing a battery electric aeroplane, the propulsive performance of the engine will vary significantly with altitude. So, in order for all the different constraints to make sense on the same chart, which is the goal here, you must use your model of how the engine is likely to respond to density altitude changes to map the constraint values you calculated to sea level static values. So, if the 30,000 foot cruise constraint demands, say, 1 kilonewton of thrust, you must plot the estimated sea level static thrust rating of an engine capable of giving you 1 kilonewton of thrust at 30,000 feet. This is typically a lot more, could be, say, 4 kilonewtons. In an earlier video, I talked about how designing on the atmosphere equals ice assumption should generally just be a starting point, and calculations and at least a verification of the design should be repeated against a range of atmospheres. ADRPi, more on which presently, has convenient features for doing this. Check ADRPi Shorts 1 for more details. And now for the main event. Let's grab a Python and an ADRPi and a piece of Jupyter Notebook, and let's sketch out an estimate of the constraints that will have driven GoUAV's wing and engine sizing. First, we need to define the atmosphere in which ADRPi is to do the calculations. For simplicity, we'll just use an ISA here, but normally you'd build multiple constraint diagrams for a range of atmospheres. Next, the design brief, specified as a Python dictionary variable. We'll base our example on the published technical spec of the aircraft. We start with the takeoff line of the dictionary. At her home airfield, she needs a ground roll of about 90 meters, so we'll put that into the takeoff line. Turn performance is next. We'll specify 2.5 G at 1,000 meters at 70 knots true. Climb. We expect the aircraft to climb about 1,000 feet per minute at 1,500 meters above sea level at its best climb speed of 50 knots indicated. Now, the cruise line can contain any steady level speed the aircraft is expected to maintain, as well as the corresponding throttle setting. We'll put in 110 knots true here at sea level ISA. Service ceiling included here for completeness, unlikely to have been at the forefront of his designer's thinking. And finally, the stall speed in the clean configuration, which, as we have seen, can set a hard limit on the wing area. Now, we'll need a weight estimate here as well to work out an actual power requirement as opposed to just a power to weight ratio, and we'll use a typical takeoff mass about 50 kilograms short of the MTOW. We next tell ADRPi what we know about the wing geometry. A simple Hershey bar planform here with a sweep angle of 0 and an aspect ratio of 7.43. And we also define at what fraction of the given weight we expect the various constraints specified above to be met. We set it to the full weight in each case here. Design propulsion just says the generic propulsion system type. Finally, in design performance, we set out our estimates of the key aerodynamic metrics of the aircraft. CDN-CL in the takeoff configuration, CL max in the takeoff configuration, CL max in the clean configuration. We also tell it what our estimate of the rolling resistance of the wheels is. 0.02 in this case refers to wheels on tarmac. And finally, eta prop is the efficiency of the propeller, and we include separate estimates here for the various phases of the flight to which we have specified related constraints. We are now ready to instantiate an aircraft concept object using all these dictionary variables we have just created. The design brief, the design definition, the performance dictionary, and the atmosphere, as well as the propulsion type. There's one more ingredient to the constraint diagram, which is the range of wing loadings over which we would like to plot the various constraints. Somewhere between 300 and 800 Pascal is about right for a microlight. Also, obviously, I've just tried a few numbers and came up with these on a trial and error basis. And now we're ready for some constraint diagram action. The quickest way of doing this is via a method called propulsion sensitivity monothetic. As the snappy name suggests, this can also do some funky one factor at a time sensitivity analysis on the constraints. Check out the ADRPi documentation on how to do this. But here we're just using it to plot the constraints across the range of wing loadings we specified. Setting show to combined just tells it that we want all the constraints, and we tell it that we want power required on the vertical axis, could also be power to weight or thrust to weight, and wing area in meters squared on the horizontal. We could also opt for wing loading here. And here it is. So as we have a closer look at this constraint diagram, we can see the feasible region in the top right, wherein the actual aircraft ends up just where you would expect, near its bottom left-hand corner. I'll drop a Jupyter Notebook version of this worked example into the notebook section of the documentation folder on the ADRPi GitHub page. This will also tell you how to generate a more personalized version of the diagram where you can tinker with its presentation, and most importantly, you can place multiple sets of curves, for example representing the constraints computed in different atmospheres, onto the same diagram. Also, do check out the ADRPy documentation for details on what is under the hood of these constraint calculations. There are several layers of corrections and models and estimates behind the headline numbers in each constraint, from environmental corrections to drag estimates. Make sure you understand them all as well as their limitations before using the constraints module in anger. So there you have it. An algorithm for establishing a good starting region for the scale of your design. And I stress that it is just a start. As your understanding of your design progresses, you can refine the constraints and new ones may appear. For example, the fuel tank volume requirement may end up demanding a larger wing than the approach speed constraint does. But the advantage of this procedure is that it works from the earliest point in the design process, pre-design even. For example, supporting discussions about how to construct an appropriate balanced design brief. And it can take you all the way up to final concept freeze, with the fidelity of the boundaries of the feasible space improving along the way. For your own design project, whether you'll code up your own constraints as outlined in this video, or you choose to press ADRPy's constraint analysis tools into service, happy designing!